We've seen the situation where gamma squared over m squared minus 4g over L, the discriminant of our expression for r, is equal to 0. And we've seen that the implication is simply an exponential return to equilibrium from whatever the release point. Now, let's consider the case where this discriminant, gamma squared over m squared minus 4g over L, is greater than 0. In that case, the square root of this term, I won't read it to you as I write it, is greater than 0, so that our solution for r, which is negative gamma over 2m plus or minus, left off my 1/2 again, okay, I'll just put it over 2. Will consist of 2 negative solutions. Now, how do I know that both of those solutions are negative? I determine that simply by looking at this term as opposed to this term. If g is greater than 0, what we have under the radical is going to be less than gamma squared over m squared, which means that the square root is going to be less than gamma over m. Now we have a 1/2 times this square root. If the square root is less than gamma over m, then your negative gamma over 2m plus that square root is still going to be negative, because this term is going to be less than this term. And of course, if we use the negative, r is certainly going to be a negative number. So we determine that r consists of 2 negative solutions, both of which are going to be decaying exponentials. Now, one of them, the one that we get if we use the minus, is going to have a more negative value, so one of these solutions is going to approach 0 more rapidly than the other. So we're going to have 2 exponential solutions, one of which approaches 0 rapidly, one of which will approach 0 less rapidly. When we superpose these 2 solutions, when we add this solution to this solution, we get something that looks a whole lot like a single exponential. But it's really going to begin to decline more rapidly according to this, and then the decline is going to be more gradual as a result of this solution. Depending on the initial conditions, we might have more of this solution and less of this, or more of this and less of this. And we're going to have a lot of variety in the kind of solutions that we can get, but they're still always going to have the characteristic that they asymptotically approach 0. We'll see more of this later, but I'll also comment that these solutions don't both have to be positive, so it's possible that this one could be positive, this one could be negative, which could lead us to a solution of this form. Now, this type of solution would consist of a pendulum which approaches the equilibrium position in much the same way as our last example. A pendulum is released and simply approaches equilibrium from one side. But it's also possible that the pendulum could overshoot the equilibrium and then exponentially slide back toward the equilibrium position. We'll see later how these specific initial conditions can give us both of these types of solutions. For right now, we'll simply stick with the conceptual idea that when this discriminant is positive, we get a combination of two exponential functions, one of which approaches zero relatively more rapidly than the other. And by superposing those two solutions, we can get this kind of behavior or this kind of behavior.